So welcome everyone to the Nuclear and Particle Physics Society seminar on the recent results from the Muon g-2 experiment. We're very grateful today to be joined by Professor Mark Lancaster from the University of Manchester. Professor Lancaster is a distinguished researcher involved with muon magnetic moment experiments, having been the co-spokesperson for Fermilab's Muon g-2 experiment, and is currently the UK's leading researcher for this project. Today we have a presentation by Professor Lancaster, followed by a question and answer session. It's a very rare opportunity to be able to meet with a lead researcher on such a pioneering and now very world famous experiment. So make sure to make use of it. The entire talk will be recorded. So if you want to ask questions afterwards, feel free to unmute yourself if you feel comfortable. But if you don't feel comfortable, pop a question in the chat and we'll read them out on your behalf. Also, while I've got your attention, keep an eye out for the other seminars that our society is going to be hosting later in the semester. Follow our Facebook page for updates. I'll put a link in the chat in a minute after this. After the talk, I'll invite you all to unmute yourselves and we'll attempt a Zoom round of applause. I think that's everything, unless, I think that's everything. So all I've left to say is thank you for joining us today, Professor Lancaster, and I'll hand over to you.
Right. No, thank you for inviting me. I get to talk to a diversity of people, but I think the people I most enjoy talking to are sort of students and people, because you always ask the best questions. So by all means, there's definitely no such thing as a stupid question. I mean, I get, everybody thinks they're a genius, the people I work with, and believe you me, they're not. So by all means, ask questions, put them in the chat, and ask anything you want. I don't guarantee I can answer it, but I'll do my best. So I'm going to discuss this sort of experiment which hit the news, I guess, about 2 or 3 weeks ago now, about measuring the magnetic moment of the muon. I'm going to give you quite a bit of history, actually, just try and motivate why we were silly enough to try and do this experiment. This experiment is taking place at Fermilab, which is a lab just outside Chicago. This is a picture of the lab. It's got this iconic building which was opened by President Nixon in 1970, and that thing that you see in the foreground is actually the superconducting magnetic coil of our experiment, that had to be shipped all the way from Long Island to Chicago, but I'll talk about that later. So let me try and, why is that not moving? So one of the principal motivations why we decided to do this experiment was that, you've all heard of the standard model of particle physics. It's an amazing model. It's mathematically elegant and compact, and it's over, the last 40 or 50 years. It's described tens of thousands of observations, but we of course know that it's not complete, because it can't explain two pretty obvious things that we see in the universe. It can't explain why the galaxies rotate at the speeds that they do. They rotate quicker than they should. So we believe that's due to an extra form of matter called dark matter. There's also dark energy there, which is forcing the universe to expand quicker than we would think, and particle physics has absolutely no idea what that is, for sure. And we've also got the slight problem that all the antimatter that was created in the Big Bang should have all disappeared, really. And we have this preponderance of matter over antimatter, or the antimatter should have annihilated all the matter just after the Big Bang, and we should have just had energy really in the universe. But we have this preponderance of matter over antimatter, which of course is good news because we exist, but we have no real understanding of why that is the case. None of the interactions in the standard model or the particles in the standard model explain either of these two things. There are also other things in the standard model which are slightly more esoteric, but sort of hint at the fact that it's maybe just an effective theory, that it's not, the most elegant, beautiful theory that it's often purported to be. A lot of these things people describe as fine-tuning problems. So one example of that is we know that the neutrino mass is extremely light. It's probably less than an electron volt, but we know that the top quark mass is 175 GeV. So the ratio of these masses is something like 10 to the 12. And that's a very unnatural ratio, which in any theories, in most theories, the ratios that you see tend to be close to unity. The other problem that we also have is that in the strong interaction, what people talk about QCD or quantum chromodynamics, we have to put in by hand a kludge into that interaction to stop it violating what we call charge parity, i.e. it has the symmetry between matter and antimatter. So there's a fictional particle is inserted in the standard model called the axion, which stops problems in the strong interaction. So we have the observation that the strong interaction conserves this charge parity operator, but there's no a priori reason why it should. We don't know, for instance, whether the neutrino is its own antiparticle or not. It may be. And of course, we have no viable theory of quantum gravity at all, or why is gravity so weak in comparison to the other forces. And we have absolutely no idea within 120 orders of magnitude what dark energy is, because we believe that dark energy is due to a scalar field or a scalar particle. The only scalar particle we know of in the standard model is the Higgs boson. If you say that the Higgs boson is responsible for dark energy, it turns out that you get the answer wrong by 120 orders of magnitude. So that's a little bit unfortunate. So there are many things wrong with the standard model, despite the fact that it has all these successes in explaining lots of data. And a couple of those, if you even just go into Wikipedia, it tells you what the problems of particle physics are. And two of those involve the muon. One is the thing that I'll talk about, and this other thing, which I will just briefly mention, this so-called problem of the proton radius, where the problem there was that if you create what we call electronic hydrogen, i.e. just an electron going around a proton, and do experiments there to determine what the radius of the proton is, which is, about a Fermi, you get a certain answer. But if you use a muonic hydrogen and replace the electron with a muon going around the proton and try and determine what the radius of the proton is, you get a completely different answer by 9 standard deviations. So that's been a mystery for many years. That may actually be just about to be resolved, actually. So the big questions are really in particle physics, and these questions have been around for 30 years, is what is the mass scale and the nature of the new types of particles or interactions that will answer these questions. So, explain dark matter and the antimatter asymmetry in the universe. And we were all led to believe, of course, that when we built the LHC, all these wonderful new particles would arise at this energy scale of a TeV, 1000 GeV, and we should have seen these new particles, and we could all have gone to Stockholm and picked up Nobel Prizes. But unfortunately, the LHC hasn't seen any of these new particles, which certainly is a little strange, but to some people not unsurprising. So my mantra has always been that rather than just relying on one huge machine in Geneva, that we should also try and build as many other experiments as we possibly can, a big variety of them, and try and make as accurate measurements as we can and see if we see deviations that way. So there are two approaches for looking for new particles. So in some ways, these are embodied in these two characters here. You've got the Einstein approach, which is the LHC approach, where you just collide particles into each other, and you can create new particles up to the energy of your colliding beams. You can add together, and you can create particles of a mass of roughly twice that energy through the equals mc squared. So you're creating real particles in these collisions. These collisions are quite messy, and you have to reconstruct what's coming out of these collisions. So that's often described as a collision of, you're trying to see how a Swiss watch works, and you're just colliding them together and looking at the debris. The approach that we're taking in our experiment relies on the uncertainty principle, this relationship that you can borrow energy from the vacuum for a certain amount of time, given by this delta E, delta T is greater than h bar over 2. So what that means is that any interaction of a particle with any other particle is then actually affected by what we call virtual particles, which are these things which can pop in and out of the vacuum by virtue of the fact that you can borrow an amount of energy from the vacuum for an amount of time and create these virtual particles. And these virtual particles, although they don't exist for a very long time, exist long enough to have a tangible effect on things that you can measure. The effect is typically at the sort of part per million level, but they have a tangible effect. So this is sort of embodied here. If you take this, the classic experiment that you always do in particle physics is collide an electron with a positron, and it creates an electron and a positron, and those particles collide head on. One has got a positive momentum, one's got a negative momentum. So their total energy is twice E. Their total momentum is 0. So when you add those two things together, you get that 2E squared is m squared c to the 4th. But then, so what you've essentially created there is a photon of mass. And we know, of course, that real photons have 0 mass. So in these experiments, we're creating virtual particles all the time. They have a mass and they're allowed to exist with a mass and a duration defined by the uncertainty principle. So just to give you a scale of the sort of time scales involved, at the LHC, they're trying to look for particles which are of the order of 5,000 GeV in terms of a mass, or GeV over c squared. And if you want to create a virtual particle of 5,000 GeV, you're borrowing quite a lot of energy from the vacuum. You're only allowed to do that for a very brief amount of time. And that amount of time is tiny. It's about 10 to the minus 28 seconds. But it's actually long enough to affect things in a tangible way. And that's what we see in our experiment. We see these small changes in the magnetic moment. So the measurement that I hinted at briefly of maybe there's also something strange happening with muons with the proton radius puzzle. This has been around for the best part of 10 years. And in some ways, this is a salutary tale of that you should never really necessarily believe the previous measurement that somebody else has done. There tends to be confirmation biases in experiments, and this has been seen in recent measurements of the neutron lifetime, whereby for 10 years, somebody measures this value, and then everybody has about the same precision, and they all seem to measure roughly the same thing. And then somebody has a great new idea of how to measure it a lot better, and then they get a very different value. And then lo and behold, all the other subsequent experiments seem to get the same value again. So it's quite a dangerous thing. And so what it looks like is that over the last 30 or 40 years, that all the electron measurements of the proton radius have actually been wrong, because there's been a new one was made last year, which now agrees perfectly with the muon measurement. So this now looks like that we've been led up the garden path by people making or interpreting measurements incorrectly for about 30 years, which is an interesting way of getting rid of new physics, that you've essentially found a systematic in your experiment, or you've done something wrong in your experiment. So that's also a worry. There was also in the news a couple of weeks before our experiment was in the news from CERN with this experiment called LHCb, which looks at B quarks, and it looks at their decays to strange quarks and charm quarks. And what they've seen is that if you compare the rate of B quarks going to strange quarks plus electrons, or going to strange quarks plus muons, they seem to get a different rate. So the standard model predicts that electrons and muons should basically be the same in this context, but this experiment has measured them to be different. And you can see that here on this plot here. The sort of horizontal axis, this pull in sigma, is basically the number of standard deviations that it's away from what you expect. So the standard model prediction are these yellow points with their uncertainties, and you can see that some of them have large uncertainties from the theory, and these blue points are all the measurements. So you can sort of crudely take an average of all of those blue points, and it looks like at 2 to 3 standard deviations, all of these measurements seem to differ from the standard model. And all these measurements are basically measurements of looking at muons versus electrons. So that's hinting that there's something strange going on. But in particle physics, we don't claim anything until it's 5 of these Pauli units of these 5 standard deviations. So nobody as yet is claiming anything from these, but maybe there's a pattern emerging that all is not well with muons. So that would be very interesting if that turns out to be true. So now just a little bit of history about just magnetic moments and what they are and how you measure them. They've been traditionally unbelievably important in terms of defining the standard model. It's often overlooked in the era of collider physics when people talk about discovering Higgs bosons and things, and people forget about these previous experiments. But there was evidence for quarks 60 years before, well, 50 years before quarks were really discovered by measuring the proton and neutron magnetic moment. I'll talk about that in a moment. And all these wise people got together in 1947 in Shelter Island. That's Feynman doing a calculation of QED in front of all the assembled people. And the reason they had to invent, quantum electrodynamics was that the Dirac theory, which was the best quantum theory around at the time, was incomplete. They found that the magnetic moment of the electron was not exactly what Dirac predicted in the 1930s, and you needed additional interactions, which was embodied in QED. So both of these magnetic moment measurements essentially established modern particle physics. They established the existence of quarks, and they established the existence of a renormalizable field theory, which is the basis of everything that we do in particle physics. So it's the analogy that people tend to use to explain what a magnetic moment is sort of here. It's not quite like this, of course, because this is quantum mechanics and not classical mechanics. But essentially, if you have a rotation of an electric charge, then an electric charge or current going around the loop creates a magnetic field. Or if you have a loop going between a bar magnet, it will rotate. There's a torque on that magnetic loop of current. And so in all of these things, what we tend to see is that if you place a magnetic moment or a charge in a magnetic field, it will rotate, and the speed of that rotation, it tells us something about the internal dynamics. And of course, from your first year dynamics, that if you have a change in angular momentum with time, or a torque introduces a change in the angular momentum with time, and this angular momentum is related, certainly in the sort of quantum world, with the magnetic moment. The magnetic moment just arises from the charge of the particle and the fact that it's got some angular momentum. And we know that in the quantum world, there are two types of angular momentum. There's the rotational L angular momentum, but there's always the intrinsic angular momentum, the spin angular momentum, which has got no classical analog. And what we're measuring in our experiment is actually the intrinsic magnetism due to this angular momentum, the spin angular momentum of the muon or the electron. And in many ways, it's just analogous. What we're doing is analogous to a gyroscope. You're probably familiar from Jeff Forshaw's great book of, if you have the axis of a gyroscope is not aligned with the gravitational field, i.e. it's not vertical, then you have this precession of the gyroscope due to the fact that these two axes don't align. You have a torque, which is this R cross G. And it's exactly the same in our experiment. We have the spin of our muon does not necessarily align with the magnetic field. And so there's a torque due to the spin, or this magnetic moment, this mu of our muon cross the B field. And we get exactly the same effects, that the direction of the muon spin, we say it processes or it rotates around the direction of this magnetic field with a very well defined frequency. And it took a while to work out in quantum mechanics in the 1920s and 30s what that frequency was. And what they chose to do in the end was parameterize that rate of precession or rotation of that spin direction by this number called little g, the dimensionless gyromagnetic ratio. And Dirac, you can see there, somewhat sinisterly holding an axe. Most pictures you see of Dirac, he looks quite calm and civil, but here for some reason he's carrying an axe and looks quite sinister. But he was the person who worked out what this g should be in his quantum field theory in the Dirac equation. And it took a lot of umming and ahhing as to whether this number was 1 or 2. There were all sorts of factors of 1 and 2 kicking around due to special relativity and various other effects. And it took about 10 years for everybody to agree that this number was 2. and not 1. One of the principal detractors of this was Pauli, who's very well known for basically slagging off everybody else's theory. So he was. This is a picture of him here when he broke his shoulder. It was a secret picture because he broke his shoulder because he got drunk and fell down a staircase in 1929 during Prohibition in America, when you weren't allowed to drink. So he had to keep it quite secret as to how he managed to dislocate his shoulder. And you're all familiar with the Pauli spin matrices, and that Pauli is the god of electron spin and all the relationships. But when the person who really came up with these ideas of spin was not Pauli, it was Kronig, and it was also Heisenberg. And when it first was proposed, Pauli basically said this was nonsense, and he just ridiculed the idea, mostly because he didn't think of the idea himself, right? He was very much of the opinion, unless he had the idea was probably wrong. But in the end, Pauli took all this on board, and he obviously developed this great theory and the spin matrices, which you're all familiar with. But I think it's worth remembering that in the history of all of this, it's never quite straightforward, the path of science, that doesn't quite happen. It's in the textbooks. So Pauli, of course, once they'd agreed that the G of the electron was basically 2, according to the Dirac theory, everybody started going, well, what's G going to be for the proton? And the argument was, well, the proton's just like the electron. It's a charged particle. It has a spin of a half. So the G of the electron the G of the proton is just going to be 2. It's going to be exactly like the electron. And, Pauli said there was no point even trying to measure this because we knew the results already. And Gerlach, if you know Stern Gerlach fame, this is Gerlach here eating some of the cake with Pauli. His riposte was that no experiment is so dumb that it should not be tried. So Stern and Gerlach went off and tried to measure the magnetic moment of the proton, which is very difficult because its effect is it scales with the mass, and so it's the famous 1/1836. The effect is a factor of 2,000 less than the electron, but Stern managed to do it. Stern was also a bit of a maverick experimentalist. He did things pre-health and safety. He liked smoking cigars in the lab. One of the only reasons they managed to do the Stern-Gerlach experiment with the silver atoms was that the photographic plate was so covered in cigar smoke that they could actually see the trace of the silver atoms. It's debatable whether they would have actually seen them had Stern not been smoking so much in the lab. He was also notoriously error prone with his apparatus. There's this great quote: "You do less damage if you let things fall than if you try to catch it." But he was a great scientist. The money for that experiment actually came from J.P. Morgan. It came from the bankers in New York because Max Born was working in the physics department in Germany where Stern was. And Max Born asked Einstein to use his celebrity to tap up the New York bankers for some money for this experiment. And then you've got the great connection, of course, that Max Born's granddaughter is Olivia Newton-John. So if anybody ever asks you the question, what's the connection between John Travolta and the magnetic moment of the proton, then there's this convoluted way that they're related, but it's a sort of different era when you could actually find bankers who would give you money to do scientific experiments. But without them giving them that money, I don't think that this experiment would have happened. So of course, what happened with the proton was that they didn't measure it to be 2. They measured it to be somewhere between 4 and 6. And so that told them in the 1930s that the proton was not like the electron. It wasn't just a simple charged particle with spin. It must have some internal dynamics or some internal substructure to cause this G not to be exactly equal to 2. So that was evidence that quarks existed at least 40 years before there was any direct experimental discovery of the quarks. Stern made quite a lot of money out of this because he got all the theoretical physicists to place bets on what G would be, and they all said it would be 2. And so I think he already knew the answer, but he pocketed quite a lot of money off all the theoretical physicists. So the big change in all of this then came in 1947, as I said, when people started to measure the G of the electron a little bit more accurately, and they found that it wasn't exactly 2. They measured it to be about 2.00232, and Schwinger and Tominaga and Feynman realized that the reason that this G value wasn't 2 was because a magnetic field is just, you know that a magnetic field obeys Maxwell's equations, it obeys the wave equations. So a magnetic field is just an electromagnetic wave. It's just a photon, basically. So in particle physics, you can calculate the interaction of a charged particle with a magnetic field by just working out what the Feynman diagram is of an electron interacting with a photon. And essentially, that's what Dirac did. And Feynman and Schwinger then realized that you could also have this additional contribution. You have these virtual particles being created. So here you've got this horizontal little virtual photon going between the electrons, and you can calculate the probability of that being emitted. And it's related to this electromagnetic constant, this magic alpha, this 1/137. And you get this beautiful equation that G changes by exactly alpha over 2 pi, and that's on Schwinger's grave in Boston. So in 1947, it was known that the G of the electron wasn't exactly 2, and it differed by about 0.1%. And so people then started measuring that more. And then it was realized that, of course, the simple that is just one contribution to this G factor from one virtual particle, one Feynman diagram, one interaction. But you can conjure up thousands and thousands of these types of virtual diagrams. The more complicated these diagrams get, it tends to be that the less they contribute, but they all do contribute. And so at the moment, the number of diagrams which have been calculated is about 13,000, and it's an amazing theoretical tour de force. But basically, any particle that exists or that we know exists in a standard model can then contribute through one of these diagrams to this magnetic moment. And of course, the argument then goes that there may be new particles which we don't know about, which can also contribute to this. And that's the motivation for us doing this particular experiment. When you get to some of these diagrams, particularly in quantum electrodynamics, don't look like any Feynman diagrams you've ever seen before. I mean, you're used to seeing relatively simple Feynman diagrams at what is called leading order in perturbation theory. These are diagrams at the 5th order in perturbation theory, and they look more like works of art than they do Feynman diagrams. But Kinoshita and his colleagues at Cornell have calculated each of these 12,792 of these Feynman diagrams and got a number out, and it's a remarkable theoretical achievement. So it was also realized, of course, that while we can measure the G-2 of the electron much more precisely than a muon, because an electron is stable, it's easier to manipulate and measure than the muon, that typically what happens, if you postulate that a new particle exists, we just call it particle X, a new type of particle, it could be a dark matter particle or whatever you like, that will affect your magnetic moment, typically with the ratio of the mass of your lepton, so the mass of your electron or your muon, divided by the mass of this new particle squared. And so it turns out that if you want sensitivity to high values of your mx, because you've got this higher mass of the muon entering into this effect, it magnifies the effect compared to the electron, despite the fact that you can do the measurement of the electron a little bit better. But it took at least 10 years for them to come up with a method to even work out how to measure the G of the muon. And after 10 years, they just said that it was 2 plus or minus 0.1. So they weren't even sensitive to this one Feynman diagram virtual correction, this alpha over 2 pi correction. That took several years for them to get to that thing. So one of the great things that we have in the weak interaction is the force which mediates the muon to decay via a W boson. And it has a remarkable property. If it didn't have this property, we would not be able to do our experiment, because, as I said, what happens when the muon is in this magnetic field is that its spin, the direction of its spin vector, rotates around the magnetic field. But spin is not something that you can directly observe in the lab. But it just so happens, and this is lucky, it's a property of the weak interaction, that if you let a muon, or positive muon in our case, decay, then the direction, due to the conservation of angular momentum and the way and the structure of the weak interaction, it so turns out that the direction of the highest energy positrons follows the direction of the muon spin. So if you can just have detectors which measure the rate, the time evolution of these positrons and look at the highest energy ones, you will see that it goes, if you had a fixed detector, say to the right, red boxes, when the spin of the muon rotates away from the detector, you don't see any of these high energy positrons in your detector, but when the spin is pointing towards your detector, you see them. So you see this modulation of the number of these high energy positrons with time, and that is just telling you the frequency at which this spin rotates. So that is very lucky. This all happens obviously relatively quickly. The muon decays in 2 microseconds. In our experiment, the lifetime is dilated by about a factor of 30. So the muons live for about 64 microseconds. It doesn't sound like a long period of time, but in particle physics, that's an infinity, because most of our devices and detectors that we use are good to a few nanoseconds. And so a microsecond is a huge amount of time. So just to put some equations onto this, I won't go into all the equations. As I said, we've got this spin angular momentum is rotating around. But what we do is we have to keep our muons in a magnetic field. The easiest way to keep your muons in a magnetic field is to have a vertical magnetic field. And then you've just got the usual Q, V cross B is mv squared over R. Our muons just go around in a circle. The centripetal force is provided by the magnetic field. And so when our muons are going around this magnetic field, they're changing direction. And so their momentum is changing, or the direction of the momentum is changing. And also the spin direction is changing. It's processing around the magnetic field. And the rate of these 2 rotations is ever so slightly different. In the Dirac theory, where G is 2, these 2 rotations occur at exactly the same frequency. But because we have these extra virtual particles, we have the spin processes a little bit quicker than the momentum rotates around. And so we have this difference in frequencies in effect. And it turns out that the difference in those 2 frequencies is very simply related to this G factor by this formula. So if we can measure the difference in these frequencies and the magnetic field to, a part per million or better, then we can measure this G, or this G minus 2 over 2 is what we actually measure. So this is what they started to do. They did an experiment just like this in CERN in the 1960s and then the 1970s. And again, there's a history of these things, of theoretical physicists thinking that they already know the answer and telling you that you shouldn't do the experiment. So before they did this experiment, they believed that the only interactions were QED, were quantum electrodynamic interactions. And so they said there's no point doing the experiment because we know what the answer is, just like Pauli thought he knew what the magnetic moment of the proton was. And of course, they were wrong again, because it turned out when they made this measurement that it didn't agree with quantum electrodynamics, because there were particles from quarks and gluons, or what generically called hadrons, and that changed this magnetic moment quite significantly. So they were wrong again with predicting the moment. So these experiments evolved. The first 3 experiments measuring the muon G-2 were at CERN. The first one had 5 people, the next one had 10 people, the next one had 20 people. The Brookhaven experiment, which is very similar to our experiment, had 100 people, and our experiment has about 200 people. The LHC experiments have about 7,000 people. A good rule of thumb is that to build any of these experiments, you need of the order of $1 million per. So our experiment costs somewhere between $50 and $100 million. The LHC costs, $3 to $5 million. So you need a lot of money to do these experiments, and you can see that the precision of these experiments hasn't followed a nice linear path downwards. It's got progressively more difficult to make these measurements. Some of that ingenuity in the technology. And there's certainly an effect that I think that if you add more people to a project, it doesn't necessarily make the project proceed easier. There's this software law that if you add human resources to a late project, it makes it even later. So, and some of the impetus was taken out of this in the 1980s because the precision that these experiments could reach was about 10 parts per million. And it was realized that in order to be sensitive to the masses of virtual particles that the colliders being built were sensitive to, which they were sensitive to about 100 GeV particles, you would need to get down to a sort of 1 part per million level of precision, which is where they achieved in about the year 2000. And we're trying to achieve a precision about a factor of 10 better than that. So just to put those precisions in context, here are the measurements that people typically make at colliders. They measure the top quark mass, the W boson mass, the Z boson mass. They all have uncertainties of tens to tens of thousands of parts per million. And here we're trying to make measurements at the 0.1 part per million. You see the electron G-2 has got a spectacular uncertainty, but as I said, it doesn't quite have the sensitivity to these virtual particles that the muon has. So this measurement that we're making is the most precise measurement that you can make at a particle accelerator, which of course makes it difficult and people think that you're slightly mad to do it. So just to bring all those numbers together, if you add up those 13,000 Feynman diagrams, you can get a very precise prediction for what this G-2 is. I mean, it's basically taken them 70 years to make this, finish this calculation. They got together again in the summer to agree a number before we published our number. And you can see how it's all built up. We've got this factor of the alpha over pi from Schwinger and Feynman comes in at the sort of 4th decimal place. But then all these other interactions, the interactions from the hadrons, the quarks, which is where all the work is theoretically, comes in. And what number is that? About the 6th or 7th decimal place. But this is important because that's the precision at which we can measure it. So our experiment is shown here. This is a motley collection of people. That's our building in Fermilab. We've got about 200 people in 7 countries. We've been at it about 10 or so years. This is one of those days where it looks like a beautiful sunny day, but this was actually February in Chicago and it was about -15. So there were some brave people who weren't fully wrapped up there. So in order to produce these muons, you need quite a lot of infrastructure. Obviously there are muons going through us all the time from cosmic rays, but we have to produce muons of a very specific energy of 3.1 GeV. And the way we do that is we start off with a bottle of hydrogen gas. We ionize it. That creates protons. They go up this thing here called this LINAC, this linear accelerator. And then they go into this thing called a booster. They're then accelerated from about 1 GeV to 9 GeV. And then these muons are not, they're all jumbled together, if you like, and we need to put them in distinct bunches such that they arrive at our detector at very distinct times. And then we have a gap between them such that we can accumulate the data. So they go into this thing called the recycler ring or the main injector to get them all bunched together and have the right time structure. And then they come back towards the main building and they come back into this thing called the muon target and delivery ring. And each of these 3 buildings in this sort of triangular type ring, one of them has a target in there. So the protons then hit a target, they produce pions. The pions go around this ring again, and as they're going around this sort of triangular ring, they decay to the muons. And then finally, we fire the muons into this building here, this G-2 building. So it's quite a lot of gymnastics, but I think from the time that you ionize the hydrogen to the muons arriving in our detector it's a few microseconds, but it's all completely synchronized. So here you can see a picture of the beam line. The beam comes in at the sort of this bottom picture here. The beam comes in at the sort of top left of there, and it comes into this, this blue device is basically our magnet. And so just to give you an idea of the numbers that we're talking about, these muons come in for we measure the decays of these muons for about a millisecond. and we do it every 10 milliseconds, 24/7. It's a very inefficient way of producing muons from hitting protons on a target. For every 10,000 muons that we get into our magnet, we've had 10 to the 12 protons colliding with the target. So it's not a very efficient ratio of converting protons into muons, but it's enough for us. And at the moment, our first measurement, we looked at about 10 billion muons. We've presently got about 40 or 50 billion muons already recorded, and we're trying to get to about 200 billion muons. So this produces a lot of data. We produce about a terabyte of data an hour. So you can imagine this is also quite challenging. We have, petabytes of data. So I'll just give you a quick tour of how then we make this particular measurement. There are a number of issues of getting this beam into this magnet. The thing, of course, is that we have a hole in the magnet allowing the muons to come into the storage region inside the magnet. And what we have to do is cancel the magnetic field while it's coming in at this angle at the top. Otherwise, they would just spiral inwards and we'd lose them. So we need an anti-magnet, if you like. We have another magnet which provides a cancelling magnetic field. So that took about 8 years to build. We then have the problem that when these muons come in, they're not in the center of the magnet. They're towards the outside of the circumference of the magnet. So we need to give them a little kick when they get to the 3 o'clock position to put them on the correct orbit. And that needs a voltage kick to move them onto that orbit, but it's a big voltage. We have to provide 3 lots of 55,000 volt pulses in about 100 nanoseconds. And if you've ever tried to do anything with high voltage over a few thousand volts and doing it quickly over a time scale of nanoseconds, you can imagine that's quite difficult. So we had quite a lot of difficulty with that, with these things sparking and various other things, but we eventually got that to work. You can sort of see the infrastructure here. There's these giant cables that come in from the top. They're basically providing this very pulsed voltage of 55,000 volts at 3 places in 100 nanoseconds just to give our beam this little kick. The other problem we have is that when our beam goes around, it actually starts diverging in the vertical direction. And so we have to have some focusing to confine it. Otherwise, it would just hit the ceiling of our vacuum chambers. So we use that using an electric quadrupole field. So we need to provide a 20,000 volt signal to these quadrupole plates to provide this quadrupole field. That again is also not straightforward. And we also need to know where our beam is going. And for that, we had to build special little detectors. You can see these here. These were built just up the road in Liverpool. They're called straw tracking detectors. When the muon decays, it produces a positron, and it goes into these things, which are basically like drinking straws, but they're very thin walled drinking straws with a gas in the middle and an anode, and it ionizes the gas and produces a signal. And then by going through these straws in sequence, we sort of do a Hawkeye style extrapolation back, and we can work out where the muon actually decayed. And so all the equations of this are relatively then straightforward. It's very much first year dynamics. As I said, we've got a torque, which is the interaction of the spin or the magnetic moment with the magnetic field. This torque causes this spin to precess at a certain rate. We have the particles going around our accelerator defined by V cross B. And then this electric field and the magnetic field come together. And what happens there is it's like simple harmonic motion or a spring, that if we're at the perfect radius in the middle of this magnet, then there are no forces on the particle. But if they deviate ever so slightly away from that perfect radius, there's a restoring force back to equilibrium. So what happens is the particles wibble backwards and forwards as they go around this ring. You have to add in some special relativity into this, unfortunately. So the actual formulas that you see have gammas in them and beta gammas, which you're familiar with from special relativity. And it's all calculated, obviously, in the great book by Jackson, the classical electrodynamics book, on page 561. It's a bit, but this is an old expression. It was also done many years ago. So if you look at how the beam actually moves, it does this sort of thing. It moves in and out radially, and it moves up and down vertically, and it does this sort of quite complicated dance of where it is in the magnet. So it's not always perfectly in the middle of the magnet, and the magnetic field changes as you change in the radius. And so we need to know at all the times where the muons are, how they're moving, and how the magnetic field is changing. And that's the difficulty really in this particular measurement. So this is an illustration of what I was saying earlier of how we've got this red arrow here, which is our spin vector rotating. And as I said, when the spin vector is in a certain direction, the positrons are going in that direction. And if we then look at the high energy positrons in that direction, we know that the spin is in that direction. So what we see is that the number of high energy positrons just goes up and down with time, as sort of embodied really here with this bit of this blue curve just going up and down. And the rate that those number of positrons goes up and down tells us the rate that this spin vector is rotating. So you can see that here, this is us taking data. This is muons coming in, and you can see it's got this, we call it a wiggle. So this wraps around in time. This is in microseconds. And you can see that in a few minutes or an hour, we have, millions of these decays. And you can see this signal of the wiggle of the number of these positrons increasing and decreasing with time shows up pretty easily. It's got an exponential suppression because the muon is decaying. And to first order, you can then just fit that distribution with a 5-parameter fit. So you can do it in 3 lines of Python and extract your value of g-2 with a reasonable accuracy. But for the accuracy that we need, it's not quite enough. So just to quickly just on the detectors that we use, we measure these decay positrons in what are known as calorimeters. They're basically lead fluoride crystals. When the positrons go in these crystals, they glow a nice blue color, and we measure the light, that blue light, in what's called silicon photomultipliers. So we have 24 of these calorimeters on the inside of the ring. So the particles go around, and then when it decays, they spiral inwards and are measured in these calorimeters. As I said, we reused the superconducting coil from a previous experiment at Brookhaven. There was no mechanism to get that coil to Fermilab by road easily. So the only way we could get it to Fermilab was to ship it all the way around Miami and up the Mississippi River through New Orleans all the way into Chicago. It took about 2 months to do. It was a very nerve-wracking thing. It cost a couple of $1 million. It arrived at our experimental hall in about 2016. And what we then had to do is that magnetic field is not very uniform. So we need this magnetic field to be uniform to about 1 part per million. And so you can see in this picture here, these are the pole pieces of the magnets. And if you look at the top and the bottom, you can see little bits of metal with screws in them. And those screws are just moving these pole pieces by a few microns at a time in order to make the magnetic field uniform. So we essentially went around this magnet and did nothing else but for 2 years, but put in these tiny pieces of metal and screwed them. They've got a thread on it, such that these giant pieces of metal were moved by tens of microns, such that we could get a uniform magnetic field. So that was a very painstaking thing. We got some slave labor to help do this. This young lady here was a school student from the UK who came over to help us and spent 6 weeks doing nothing but creating tiny bits of foil and sticking it on the inside of the magnet. So that worked very well. So in the end, we got a magnetic field which was uniform to much better than 1 part per million. And we measured that by having a little thing called a trolley. It's basically a thing which goes round and rails inside the magnet, and it measures the magnetic field with NMR probes. So we had our first data in 2017. When the LHC had its first data, everybody was really excited and screaming and cheering. When we had our first data, we had no idea what was going on or whether we even had muons in going round our little magnet. And so everybody was just stood around looking very bemused, basically. But then, of course, we had our own LHC moment. You remember with the LHC that 10 days after it turned on, it blew up because they had a short in one of the superconducting cables. We had a similar incident at our experiment whereby if you've got a 1.5 Tesla magnetic field, you should never have a steel brick anywhere near it. And unfortunately, we did because we screwed up. And that brick then hit the magnet and it caused the magnet to quench. If you've ever been near a superconducting magnet that quenches, it lets out an absolutely deafening noise when all the helium is released and various other things happen. It's quite a terrifying noise. I was in the car in a taxi in Chicago on the way to the pub on a Friday night, and my postdoc rang me up and, oh, well, no, somebody rang her up and all I heard on the phone was, oh, shit, 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 oh, shit, shit, oh, shit, shit, shit. And that was the result of us finding out that a steel brick had hit the magnet. So it then took us 6 months to fill in risk assessment forms to begin running again. So here you can see what happens if we just do a simple Python fit effectively to these wiggles to try and extract this frequency, this omega A. We get a pretty bad chi-squared. We get a chi-squared of about 2 per degree of freedom, which obviously tells us that you have done something wrong. So what that turns out to be is that if you don't account for all these various simple harmonic motions of the beam, this radial and vertical motion of the beam, then you don't get the right answer, basically. So you have to add in other parameters which tell you how the beam is moving as it goes around. So this 5-parameter fit actually becomes a 24 parameter fit. But basically we're just fitting this exponential wiggle with 24 parameters, and one of them is the parameter that we know. And we essentially know that we've got this thing to do the right thing, because you can do this remarkable thing called a fast Fourier transform, which looks for frequencies in distributions. And once we've corrected for all these various simple harmonic motions and look for any of these beam frequencies, these oscillations of the beam, we don't see any when we do a Fourier transform. And we also get a chi-square per degree of freedom, which is, is very close to 1. It's 4,167 over 4,132 points. So basically we do all that and we extract our number. We've got 12 billion muons. But in order to not be biased when we were doing this measurement, because if you're doing a measurement and you've got to be very careful that, members of your collaboration don't go, wow, it'd be quite nice if we measured the number to be this, because that would point to new physics and new interactions, and then we'll all get very famous and we'll all go to Stockholm and get Nobel Prizes. So you have to stop people behaving badly, basically. So the way that we do that is that our frequency that we actually measure from that graph has an offset in it, which we don't know. And that offset is due to a reference clock system, which defines the ticks, which define our frequency. And we tweak that frequency by an unknown amount. Well, it was tweaked by somebody when we started taking data, and then they locked the cabinet and just checked it every couple of weeks to make sure it was stable. And so we had no idea what we were measuring until we did this thing called an unblinding, when we were given the offset and then we knew what our real number was. But up until that point, we had no idea what we'd actually measured. So in the gory detail of all these numbers, this is what we actually measured. You can see this number here, this g-2. It's like I said, the first few significant digits of that are just the alpha over pi. But you can see that I think, what's that, in the 7th or 8th decimal place, these numbers start diverging. And if you look at the difference of those numbers, it's, I'll never get this right. It's probably 5 times 10 to the minus 9, is it? I think something like that. And with an uncertainty of 1.2 or 50 to 12. And of course, the only thing that matters in these things is what is this difference relative to the uncertainty? The uncertainty in the theory in the experiment is about the same. And when you take the difference and divide it by the uncertainty, you get about 4.2 standard deviations. And people in particle physics get very excited when that number goes over 5. So we're not quite there yet, despite what the media said that we, discovered new particles. But what could that actually mean? I think it could mean one of 3 things. It could mean that we've been very unlucky in our experiment. There's a 1 in 40,000 chance of getting a 4.2 standard deviation fluctuation just by being unlucky. So it's basically telling us if we did this experiment 40,000 times, in one of those we would measure what we've got if we were being unlucky. It may be that our friends in theory have got something slightly wrong with the standard model calculation. I don't think that's too likely. They've been looking at that very closely. And the third one, which is obviously the most exciting thing, is that perhaps we've seen the first hints of new particles or interactions not accounted for in the standard model. So we will know whether 1 is true or not probably on the timescale at the end of 2022, because we've got much more data. So the chances that of it being a statistical fluctuation will be vanishingly small. The second thing is being rechecked by our theorists. And if 3 is true, then you basically become a meme. So this was some of the things that came out of the day that we announced this result. So we'd known this result for about more than a month. We were sitting on the number for about 10 weeks. And we managed, I don't know how we managed to do it, that we managed to keep it quiet. And I don't think we were quite expecting the number of people to join the Zoom room. And we had, 5,000 people connected immediately. Most of them weren't physicists. And then it all went absolutely crazy for the next, 3 or 4 days of everybody saying that we've, found evidence for a new particle, a new force of nature, and various other things. And about 3 billion people read all these articles, which I was quite shocked by. So just to put it in context of what it sort of means. So people are always talking about, oh, there's a 5th force or a new force of nature and all these sorts of things, right? And then what you've got to ask yourself is, well, what really is a force? And a force is a classical thing, and it's got no meaning in quantum mechanics. And this is all quantum field theory and quantum mechanics. And you'll probably know from your particle physics that all interactions, the electromagnetic interaction is just the exchange of a photon. The weak interaction is the exchange of a W or Z boson. The strong interaction is the exchange of a gluon. So when you talk about forces in particle physics, you're actually just talking about an exchanged particle. So essentially what that's telling us is that we probably, if this result is confirmed with higher statistics, then yes, we have discovered a particle which isn't in the standard model and an interaction type which isn't in the standard model. And our theoretical colleagues are unbelievably ingenious. In the last 10 days, there's been about 100 publications of people with various ideas of what these new particles may or may not be. And one of the intriguing possibilities is that the LHC, of course, is looking for very heavy particles. It's looking for particles of thousands of GeV, a few TeV. But it might be that this new particle is actually very, very light on the scale of 20 MeV or so. So what all our experiment does is measures the strength of the coupling, say this G number, this G prime here, it should be alpha really, and the mass, we measure that ratio in effect. So we could have something with a big mass and a big coupling, or we could have something with a very small coupling and a small mass. And in our experiment, we don't know what that is. So it may be that we're seeing very light particles or very heavy particles, but we don't actually know. So the theorists are predicting both of these things, and if they are heavy particles, then you might have expected to have seen them at the LHC, but nobody has of yet, but they may pop up in the LHC. So there's no shortage of theoretical explanations. So then just to finish, just to say we're still taking data at the moment. Our experiment's running actually at the moment. I was checking on it just before we started. This is at Fermilab time, so this was at 2:28. This just shows our data ticking in, and the data set that we have now is about 5 times larger than the data set which produced this number, and our measurement was statistically limited, so we should, I expect, reduce the uncertainty of this number by about a factor of 2 when we analyze the next data set, which will be more than enough to put it over this magic 5 standard deviations if nothing changes. So that's obviously exciting. So just to summarize, I think the main takeaway message is that we know that the standard model is flawed because of dark matter and the antimatter problem, and it's been very resilient with these thousands of measurements. It could well be the case that this experiment that we've been working on is showing the first signs of new interactions beyond the standard model. And I hope I've shown that in the whole history of doing these types of experiments is you've invariably got somebody telling you that you shouldn't do it because you already know the answer. And so I think we should all remember what Gerlach said to Pauli, that no experiment is so dumb that it should not be tried, and you should always try and do difficult measurements, even if your theoretical colleagues tell you that they already know what the answer is, because certainly in this case, they didn't know what the answer is. So that's the moral. I think that's all I've got for you, actually.
Wow, thank you for that. That was a really, really good talk. Wow. If I think I might be able to ask you all to unmute, and we can attempt a round of applause. Thank you.
So I'm happy to answer any questions. And as I said, as no experiment is so dumb, then no question is too dumb either. So.
Yeah, so if you've got any questions, you can put them in the chat and we can read them out, or you can just have a look if you want, Mark. And
yeah, let me stop sharing.
Or feel free to unmute yourself. I think we've got one already, actually.
Why anti-muons over muons? Yeah, that's a good question. First of all, yes. So if you just collide a proton into a target, and predominantly because the proton is a positive charge, then what you produce when the proton hits a target is you produce twice as many positive pions as negative pions, basically, and those pions decay to muon. So when our proton hits the target, we produce twice as many mu pluses, anti-muons, as mu minuses, and we need as many of these as we can get. So that's why we use those. We would also like to do the measurement with negative muons, but it will take longer, and we have to reverse the polarity of all the magnets and all the quadrupoles and everything. So it takes about a month to reverse all the connections. Why can't the muons be kicked twice? Yeah, so they could be kicked. Yeah, they could. Well, you have to give them a certain amount of a kick, otherwise they won't get round again. So you've basically got to kick them on the first time they go round, because the dynamics are such that if you don't give them enough of a kick on the first time, then they don't make it round again. Basically, they spiral out before they've got round once. So we do actually, because this pulse that we create, this 160,000 volt pulse, isn't a perfect pulse, as you can imagine, and it's got ringing, so it goes up and comes down over 100 nanoseconds, then it wibbles up and down for a while, and that's a problem because it is giving little tiny kicks as the muons go around the next time and the next time and the next time, and we need to know exactly what those tiny little kicks are. Those kicks aren't sufficient to kick the beam out, but they are sufficient to move it in and out of where we think it, of the perfect place inside the magnet. And so, yes, we need to know what that is. That took us a year to measure that. That was frustrating. Let me go up to
there was a question just before that.
Yeah.
Why do people refer to measuring G-2 and not simply G?
Yeah, it's basically comes down to that equation. Maybe I should share my screen and show that equation again. Let me go back. Where was I? Where was that equation? I've probably lost it, haven't I? It's basically this equation that it's G minus, because the difference in these frequencies is G minus 2. It's not G, basically. And so it's only, you get this nice relationship between the frequency that we measure and the magnetic field is defined by G minus 2 and not G. But in effect, we are measuring G. But it's sort of just a convenient mathematical trick, really. What are some possible explanations for the difference? Yeah, like I said, I think there are two. So when I talked about this, also this experiment at CERN called this LHCb experiment, which has seen these B quark interactions with electrons and muons being slightly different, it gets slightly difficult then to have something which explains both of those observations. But the particles which people talk about are things called Z primes. And all a Z prime is basically a heavy photon or another. So the Z boson in some ways of the weak force is in some ways a heavy photon. It's a 91 GeV photon. And so one of the simplest extensions of the standard model is to say, oh, maybe we've got two Z primes. We've got the one that's in the weak interaction, and maybe we've got another one which is in the new weak interaction. You know, there's another weaker interaction with another Z prime in it. And the mass of that Z prime could be very heavy. It could be 10 times the mass of the Z that we know, or it could be 10 times, you know, it could be 1,000 times lighter. So that's one of the things. The other thing that people propose, which is theoretically is not a very attractive idea. My friend Jeff Forshaw hates them, but they're called leptoquarks, which is a weird fusion of a lepton, i.e. an electron, and a quark. It's some sort of weird composite object called a leptoquark, which people invented in the 1970s to explain why the proton does decay. Well, the proton's got a lifetime of 10 to the 32 years, but it should decay and will decay. And one of the simple ways that it would decay is by emitting these leptoquarks. So they became a popular thing. And so the leptoquarks you can see come in because in the LHCb experiment, you've got these B hadrons or these B quarks, and you've got something weird happening with electrons and muons. And so you need an object which couples differently to electrons and muons, and all the things in the standard model all couple the same to electrons and muons. It's just a fixed number. And so, but if you introduce these mythical leptoquarks, you can dial it up and say, well, this leptoquark 1 couples to electrons this much, but it couples to muons this much, and so they're different. So yeah, they're not very elegant, but they fix up. There are these also things called axions, but invariably these are sort of light neutral particles, basically, what they tend to be. So I was not expecting to act to muons and anti-muons. Yeah, it is a big deal. Is there any reason, or is this that matters that much? I mean, the main reason is we just want statistics, and so the factor of 2 is the big deal. It's not exactly a factor of 2. It's about the rate is it's about 40. It's actually more. It's 40%. So it's 2.5. So would you expect some difference for muons? Yes. No. That's the measurement that people would love to make of the g-2 of the tau. The problem with the tau is their lifetime. I'm going to get this wrong now, aren't I? What's the lifetime of the tau? It's a picosecond, isn't it? It's something like that. So they're very tricky, right? So if your thing only exists for a picosecond, then you're not getting it in a little magnet and it going around a few hundred times. But taus do decay, and in the same way, the direction of the decay products again does tell you something about the direction of the spin. And so you can get some very crude information of what the g-2 of the tau is by looking at taus produced in colliders at the LHC. And people have tried to do that. And I think that they measured that the G was 2 plus or minus 0.1 or something. Or they may have even meant to be 2. But I mean, it was a terrible measurement. But there are people beginning to think about that, because in the same way that I said that the new physics effect comes in as the mass of the lepton squared, and the mass of the tau is much heavier than the mass of the muon. So the new physics effects could be very much enhanced in taus, but you need to measure it. You've probably still got to measure it to 1%, but I haven't done the numbers, but let's say you've got to measure it to an uncertainty of 1%, and they're nowhere near that at the moment because they decay so quickly, and there's no easy way of producing them in large numbers. So, but it would be a great thing to do. So you should, yeah, you should all go away and think how you could do this experiment with taus and get your $50 million, and then bingo, you'll be away. You'll be on your way to Stockholm in 25 years.
I've got a little addition to that question, actually. Maybe if you, because with relativity and special relativity, if you accelerate them enough to close enough to the speed of light, their lifetime would extend, wouldn't it? So could you maybe play with that a bit?
You can a little bit, but yes, you can. You definitely can do that, but because it's a picosecond, in order to get it to any sensible lifetime, you'd need a gamma factor of, let's say, 1,000.
Yeah.
And so you then need to accelerate them. You'd need to accelerate them to 2 TeV. So you'd need something the size of the LHC,
right, to
do it, right? For it to be helpful, I would say. We're even bigger, I think. You would probably need a collider about the size of the Earth to get a big enough gamma factor for it to be useful. So yeah, that's the distinct problem with taus. And taus, of course, because they're heavy, they decay to muons, but they also decay to hadrons. They also decay to pions, and that just creates a big mess, unfortunately. Right. So they're difficult to deal with, but people are definitely thinking about it. But it would need to be a very big effect, I think, for us to measure it and see it. But
something for an MPhys project for someone anyway.
It's a very good it's a very, like all these things, it's a very good feasibility study to do it. I know the Atlas experiments has people sort of thinking about it, and I think now it will gain a bit more traction because, like I said, when we started doing this experiment, people just thought we were idiots. Why do you want to try and measure something to 0.1 part per million and it's going to take you 10 years? Why don't you just sit at the LHC and wait for these new particles to be produced? But they didn't get produced, so it's yeah. So it is getting a little bit more traction now, people thinking about that. But it's a very good thing to do for a fourth-year project and try and do a sort of back of the envelope of what you would need to do to make it even, what could you get to? Could you get to a 10% measurement? Could you get, what would you need to do to get to a 10% measurement? So yeah, it's probably possible. I haven't looked at it very carefully, but I could imagine a 10% measurement's probably doable, I'd have thought.
I think there was a question from earlier we might have missed. It was, do the electric field quadrupoles have any fringe fields, edge effects that affect the calculation of G-1?
Oh, God, yeah, that's a great question.
Is that accounted for with the fast Fourier transforms?
Oh, God, yeah, oh, my Lord, yeah. So those quadrupoles are a pain because they spark. So all the time, because they're in we have to have a very, very good vacuum. We've got a vacuum of 10 to the minus 9 atmospheres in order for those things not to spark, which is a real pain. And yeah, so there are fringe fields from the quadrupoles. So we have to have an estimate of what the effects of that is. But mostly we do that by just measuring where the beam is in these little straw detectors. So, and then we simulate it to make sure that makes sense. But mostly we take that straight from the data. The bigger effect is that when these things pulse, they're doing they're creating a voltage and things start vibrating. So the quadrupole plates actually vibrate at a certain frequency because you're pulsing them with an electric current at a certain rate, which causes them to pulse. And we have been a bit unlucky and been quite close to the resonant frequency, the mechanical resonant frequency of these things. And so our quadrupole plates move slightly. Every time they're pulsed, they wobble. And when they wobble, they create a magnetic field. And so actually probably the biggest systematic of the current measurement is the residual magnetic field created by those electric quadrupole plates wobbling. And so we found that, and again, that's taken us a year to measure that and work out what it is. So in the context of our measurement, I think of it in parts per billion. The statistical uncertainty of our measurement is about 430 parts per billion. And this effect from the wobbling quadrupole plates is about 70 parts per billion. So it's much lower, but if we want to, every time you want to make the measurement better, you've got to then, mitigate these effects. So we've installed sort of little damping devices to change the frequency of this vibrations such that it's not so close to the resonance and things like that. But yeah, all these effects are difficult. And the equation that I showed has a beautiful cancellation, because obviously you know that if you have a particle moving in an electric field, it looks like a B field. And so our quadrupole field in some ways looks like a B field, but but at one particular energy of the muons, there is a cancellation, and the B field resulting from the electric field is 0. And that's if you have muons of exactly 3.094 GeV, which is why we use that momentum, which again is another problem with the taus, because I think that number then is a strange energy which is hard to produce. So there's been a lot of talk. Is the LHC have similar effects been observed with electrons which have longer lifetimes? Well, the electron has no life. Well, the electron is stable as far as we know. And so the problem with the electron is that you need to predict what the G-2 of the electron is. And nearly all the interactions which contribute to the G-2 of the electron are these QED, electrodynamic interactions. And so you need to know our friend alpha 1/137 very precisely in order to predict what that is. And so traditionally what people have done is they've measured G-2 of the electron, they've done the calculation, and they've taken the calculation and the measurement to work out what alpha is. So G-2 of the electron has been used historically to calculate alpha. But if you want to use G-2 of the electron to look for new physics, somebody else has got to tell you what alpha is. And so there's these experiments using cesium and rubidium atoms of transitions, atomic transitions, which have just been measured, which have now measured alpha pretty precisely. The problem is they differ by nice standard deviation. So nobody can agree what alpha is. So the electron G-2 is plagued by nobody knowing what alpha is. So which may be telling us something as well. So there may be something going on. There may be something going on there. Is the LHC called because the collider is large? Yes, Large Hadron Collider, not because it's large hadrons. No. How long did it take to prepare the presentation? Oh God, that's an interesting question. Not very long, because I've been working on this experiment for 10 years, and so you just piece together different slides all the time, and it just gets added together, and you just stitch it all together over time. So, and then every time you give it, you add 2 more things to it or something. So it just evolves over time. It's osmosis. So 10 years, yeah, to write the talk, yeah, basically, yeah. Everything takes 10 years. Everything takes 10 years in particle physics. So
we'll have to have you back every year just for them extra 2 slides for 5 minutes.
The best thing is I'm quite a lot of my slides. Other people then steal my slides, and I see them giving talks, and I see pictures, because I know I've created the pictures or run some code to create the pictures. Then you see it in their talks, you go, oh, that looks very familiar. You never get the credit, but anyway, it's nice actually when people steal your things and use them.
If anyone's got any more questions and they want to do it, they want to unmute themselves and do it over the video, just put your hand up if you do the raise hand feature, and we'll do that. I had a question just while we're seeing if there's any more. Yeah. If you finally managed to hit the 5 sigma precision, have you personally got any plans? Have you got any? How would you react to that?
Yeah, the press keep asking me that, and because I got loads of jip off, what's the guy called, Pauli Ghosh from the BBC, because he interviewed me, and he kept saying, can't you look more excited about this? And I said, no, I can't. He says, I've never seen anybody less excited about something which might be this exciting. So I sort of had to explain to him that, one, I was a northern male, and you just don't get excited. And in some ways it's your day job as well. It's my day job. I've been doing this for years. And you don't really notice it, and everybody's going, God, it must have been amazing. And mostly, no, you're just knackered and glad that you finished the work, and it was a lot of work. And yeah, I think everybody else is much more excited than we. Well, some people in our experiment were very excited, but I think I was just too tired to be excited. So to be honest, and I'm a cynic as well. I know I'm a cynic, so I was very surprised when the number came out to be what it was. I thought that we would find that the previous experiment had screwed up, and we'd measure the standard model. So I was very excited. Well, I was very I was sort of surprised when it came out where it did, but that's just the way it does, you know. So
yeah,
that's why we do this blind analysis, which is good, right? And what we also did is we had independent teams doing parallel analysis, doing it slightly different ways, and they were all given blind offsets as well. So you can't have team A going, I've measured 27, what have you got? And they go 26 and go, oh, well, we must be right then because they agree, right? And that's really dangerous. So they had no means of comparing their numbers either. So one of them would say, I've got 78. One would say, I've got 11. And there was no means of, you know, you don't want to, there's confirmation bias and unconscious bias and all these things. It's potentially a very dangerous effect.
Is that common practice within physics? Because I've not actually heard of that on other experiments.
It is now. It didn't used to. When I started doing these things, it was much more corrupt. It was like, well, let's have a look at the number. Does it? Oh, it looks quite good. Let's keep that value, shall we? You know. And now nearly everybody tries to do this now. But there was a bad incident at the LHC about 3 years ago when one of the big experiments, CMS I think it was, said, oh, we found this resonance at 750 GeV of going to 2 photons. And they released what the mass was. They said it's 750. And then the other experiment goes, well, let's have a look around there. Oh, we've seen something at 748. You know, and then it disappeared. So both of those were 3.5 standard deviations. So together they were about 4.2 standard deviations, i.e. the same as ours, and it disappeared. And what they should have done, I think, was they should have said, we've seen something at 750 plus or minus 200. Now you guys go and have a look at it and tell us where you think it is. You don't tell them where to look, because you'll always find something, right? I mean, so people have got a lot more aware of these effects over the last 5 years, and so it's now common practice. It's quite difficult to do though in some ways of how you actually blind it such that you don't look, because you've got the data. We had the perfect way of doing it because we measure a frequency, so we need a clock with a reference frequency, and we can just change that reference frequency in hardware with a screwdriver, and we're not told what it is. So that was the perfect way of blinding, because there was no way of getting that number. But it is quite common now.
Mm.
So what's the bottleneck on the measurement when it comes to data collection? Is it like maximum data take on the text processing level by production of muons? It's a bit of both, actually. It's one of it is the stability of all these pulsing devices, these quadrupoles producing the 20,000 volts, this kicker magnet producing the 60,000 volts. They often, you know, break. And you have to go and fix it. The data acquisition system, which is largely what I was working on, like I say, is taking a terabyte an hour and processing it. And we've got loads of GPUs and various other things. So that takes constant babysitting, because anytime you run hardware at that rate, it will go wrong. So yeah, there's a bit of babysitting. So it's mostly that. And actually, it's not really the production of the muons, because if we produced any more muons, we'd be producing data too quickly and we wouldn't be able to process it. Because it already takes us, just to go through the data and get it into a format where you can produce one of those nice little wiggle plots, it takes many months and thousands of CPUs, you know, distributed around the world to process the data. So we have to send, you know, petabytes of data around the world to process it and get it back. So that's the bottleneck probably. If there is actually a new force, do you have any idea as to whether it is an entirely different fundamental, or could it be another aspect of a known interaction? It's difficult to say what a new interaction means, because like I said, like the most common idea is that this thing is just like it's just a light or a heavy version of the Z boson. So in that respect, it's probably very similar to an interaction that we already know. It just happens to be mediated by a heavier or a lighter particle with a different rate. If it was a leptoquark or something like that, then that really would be something different. That would be wild, I think. That would be a very different theoretical idea, but nobody, I think, really knows. Could it be another aspect of a known interaction? Yes and no. I mean, you can say what electromagnetism is. Electromagnetism is just a photon, or plus the Z boson if you talk about electroweak interactions. So maybe you just say, well, the electroweak interaction, which we thought was just a photon and a Z boson, is actually a photon and a heavy Z boson and a light Z boson, and we just call it the new electroweak interaction. Most things are just, are evolutionary, are step changes in what we know. So yeah, you could look at it like that as well. That wouldn't attract the headlines, I don't think. You would basically say, no, guess what? We've just tweaked something. We've, the standard model's got 140 terms in it. We'd had 2. Doesn't sound so glamorous then. You can't go around saying we've discovered a 5th force if all you're adding is 2 terms into a Lagrangian. Could it maybe, yes, yeah, well, could it maybe relate to the fact that antimatter might be slightly different to matter? In this case, no, because for matter to behave differently than antimatter, it has to violate this thing called charge parity, this CP concept, this CP quantum number. And the interactions which contribute to g-2, by definition in the theory, conserve CP. So unfortunately, this wouldn't tell us anything about antimatter. However, as well as the muon having a magnetic dipole moment, it has an electric dipole moment. And if we saw a non-zero electric dipole moment of the muon, that would be direct evidence of matter and antimatter behaving differently. And that would be unbelievably exciting. So we're trying to make that measurement now of trying to see, does the muon have an electric dipole moment? It's predicted in the standard model to be a tiny number. It's basically predicted in the standard model to be 0 or 10 to the minus 33 or something. And we've got a sensitivity to about 10 to the minus 19 or something like that, right? So it would have to be a big effect. But if we measured a non-zero electric dipole moment, that would be, yeah, that would be amazing. And that would be evidence for the matter-antimatter asymmetry in the universe. And everybody would, even I would get excited then. Probably, well, maybe not. But there's only a handful of people doing that. My PhD student's working on that. There's a few of us working on that, but it's not the main measurement of the experiment, so it just takes a long time.
If we don't have any more questions, I've just got probably one more, if that's all right.
Sure, yeah, of course, yeah.
Do you know of any other sort of, right, so for example, whenever you've got like a big experiment like this, especially when you're getting a lot of data, there'll be other areas of physics that might be interested in the data that you might not necessarily think of. Do you know of any sort of research areas that might be using this for things that you wouldn't, might not be directly associated?
That's a good question, actually. People use muons for other things, right? There's this thing called muon spin rotation, which is, people use that to image material. So people use muons for other means. But in terms of, say, something coming directly out of our experiment, what tends to be the clever stuff that we're doing is, which is also what they're doing at the LHC, is how we process the data so quickly, because everybody, bankers want to process data in a nanosecond so they can diddle the exchange rate and make a load of money, right, on, nanosecond trading and all this nonsense. So we use these devices called field programmable gate arrays, FPGAs, and we're also using GPUs and CPUs. And the holy grail of modern computing, apart from quantum computing, is to have an easy device where you can have an FPGA which does simple things unbelievably quickly, and a GPU does things in parallel unbelievably quickly, and a CPU does complicated things slowly. But if you can combine all those things together and have a means of them talking to each other, you've got the world's perfect computer. And so we do quite a lot of things like that, where we're trying to, write algorithms on these so-called FPGAs and, and GPUs, and try and mix, all experiments are trying to do this. And Microsoft are interested in these sorts of things as well. So we get help from those sometimes. So it's more on that side of it in terms of, an application where you go, this has got, something which will, help with cancer or something. There's nothing like that. So,
right, yeah.
Which the politicians don't like that answer, of course, right?
Well, if there are any more questions, feel free to put them in the chat. But I think if there are no more, we'll do a final round of applause if you all want to unmute. Thank you.
Thank you for your questions. They're great questions.